Hello and welcome back. So today I want to continue talking about shielding by looking specifically at electric field shielding. So unlike shields for magnetic fields, a shield designed specifically for electric fields has certain characteristics that need to be taken into account if you want to design an efficient shield. So what I want to do today is look into how the shield made for electric fields is supposed to work, what are the theoretical considerations behind it, but also look at this sort of shielding in practice. So to see how the theory actually applies to the practical shield. Because in the end, if you want to make a good shield for electromagnetic waves, well, you need to make a good shield that works for magnetic fields and for electric fields. So if you're curious, then keep watching. So first things first, how do you generate electrical fields? Well, what you need is a couple conductors driven at different voltage potentials. So this can be a static voltage difference, so a DC source, but what we'll be more interested in today will be AC sources. So the electric field will be generated between the 2 points of different potential, and the intensity of the electric field will be dependent on the voltage amplitude. So larger voltages will create stronger electric fields. Now it's important to observe that between the two conductors there's certain capacity. So the electric fields are mainly capacitive phenomenon. And what's important to notice about this is that the equivalent impedance of a capacitor is frequency dependent. So the higher the frequency, the lower the impedance of the capacitor is. Meaning that if there's a certain current passing through these electric fields, the current will be stronger with higher frequencies. So you will start to have more and more problems because of electric fields as frequency increases. Now, it's important to observe though that your electric fields won't just close where you want them to close, but they will go to any nearby conductor with which there's a voltage potential difference. So if there's any sort of sensitive circuitry, some of the fields that hit it might end up causing problems. And we can see just how this system would work with today's experiment, in which I'll be using my spectrum analyzer with its tracking generator. So the noise source will be represented by the tracking generator, and the spectrum analyzer's input will be our sensitive circuit. So this way we can measure just how strong our fields are coupling and creating issues. So this is the setup that I will be using for today. These are two parallel plates, so printed on two PCBs and connected to SMA RF connectors. And these will be connected to the spectrum analyzer. So right now I have a normalized input running at -12 decibels, and if I plug in my board, and everything is screwed in nice and tightly, we see our clear capacitive behavior. So we see our nice rising ramp that goes higher and higher as frequency increases. Now I have a bit of wiggle here in the measurement, and this is mainly because of my impedance mismatches, so this thing is not a 50 ohm system, but for today's measurement this will be good. So one more thing to point out here, the measurement is performed from 100 kHz up to 400 MHz. So above 100 MHz we start to have some issues, but it's okay. But anyway, we can see our electric fields coupling. So our system will be good enough to try out our experiments on. Now in the previous video concerning magnetic field shielding, I used a setup with two inductors, one to represent the noise source, the other the sensitive circuit, and shielding was provided by conductive plates. And now what's important to mention about this is that when I placed the conductive plate in between the two inductors, the plate was never grounded. So there was no wire going to ground, or there was no clip behind the scenes. The plate was electrically floating. And for magnetic fields at least, that's not really a problem, because all the currents induced into the plate stay inside the plate. So the eddy currents are closing in through the plate, and whether this thing is grounded or not, for magnetic fields at least, doesn't matter. The effectiveness will be exactly the same. So how will this work for electric fields? So now the first thing to add to our reference setup is a PCB that has the plate of copper that is not connected to anything. So this will be our floating shield. Now if I place this close to one of my pads, so not touching, and we look at how the measurement evolves, we can see that it slowly went up. So not by a lot, so just a few decibels, but the coupling is now stronger. And that's not something we want. Main issue is that, well, our floating shield is coupling quite well with our initial noise emitter and thus creating stronger electric fields to our sensitive receiving circuit. So if you add a floating plate to an electric field noise source or to an electric field sensitive circuit, well, you're gonna make things worse. So by adding a conductive plate in between our noise source and our sensitive circuit, what we can do is end up having an equivalent capacity larger than what we started off with, so without the conductive plate in the middle. So based on the proximity of this conductive plate to either the sensitive circuit or the noise source, the addition of a floating conductive plate into our system can create stronger electric field coupling. So it's usually not a good idea to leave floating pieces of metal around your circuit, whether we're talking about the sensitive circuit or our noise source. So what would happen if we would ground this thing? And to show off this effect, first of all, I'll be adding a single very thin ground wire that will be placed in between the two plates. So this will be the closest conductor to the noise source, much closer than our sensitive circuit on the other side. So if I insert this into the ground holding clip and we watch our measurement get performed, we can see that there was a significant drop. So our sensitive circuit is not perfectly protected, but we see a lower coupling than before. Now, in theory at least, the field lines coming from the noise source will hit our shield, and then any current induced will go to ground through our ground connection and will return back to the noise source. So nothing will really hit our sensitive circuit. But it's important to observe here that the field lines don't just go in the shortest path, they spread out through space. So depending on how big the shield is, some field lines might still escape and touch our sensitive circuit. So let's look at this effect with an experiment. So what I have here is a much larger plate now connected to ground, and if we insert this thing in between the plates, so first of all I remove the initial wire, we should see our coupling increase, so now there's no shielding, nothing in between, it's worse. And now if I insert this large plate, we can already see that there's a definitive drop in coupling. So I have about 12 decibels per division here, and we see a very clear reduction in coupling. So by having a much larger plate that covers a larger surface around our noise source or around the sensitive circuit, we see that there's a significant improvement in shielding effectiveness. But it's still not perfect. So how can we make things even better than this? Now, the last critical thing to mention about the shield is its ground connection. So any conductor, regardless of how small or big it is, will have some certain non-ideal properties. And when we're talking about the shield, we're mainly interested in the impedance of its connection to ground. And the main elements that influence this will be the resistance and the inductance of this connection. So now when we have a certain current passing through this impedance, because of the value of the impedance, we'll have a certain voltage drop on it. So our shield won't really be connected to ground. There will be a certain voltage potential difference. And well, when we have a voltage potential difference, we can create electric fields. So in the end, to get a shield to be as effective as possible, the connection to ground needs to be achieved with the smallest impedance possible. In an extreme case, if this impedance is large enough, well, we're back to the floating shield situation, where the shield was making things worse than, well, not having it in the first place. And to illustrate this, what I have here is a plate that's the same size as before, so the same width, but now it's connected to ground through a large area. So it's basically a full shield from the upper area where our coupling plates are down to the ground connection. So if we try out this thing in our setup, so we see our reference measurement, and if I insert this thing, so full ground connection all around with a low impedance connection to ground, we see that now we have a much lower coupling. So we still have some noise passing through. That has to do with the exact physical position in which it is, but we see a much better shielding effectiveness with this very low impedance connection from our upper shielding area to the ground point. So I centered it a bit better, I think, and yeah, we can get even better results by this. So the better you're protecting your noise source, the better you're closing it inside the shield, the less of the fields will pass through your shielding. So now, just to summarize all of the measurements, I overlap them to create this graph. So what we see here, well, is a slightly blurry image, but behind all that we see the 5 measurements that we performed. So in pink we see our reference, and we can see that with blue we have our floating plate measurement. So this is where the floating plate was added, and we can see that this is a few decibels above, so there's 12 decibels per division, so let's say about 3 decibels more. Then our first noise emission reduction measure was the added stick, so this was the very thin line of copper, which does start to help, so this is about roughly 6 decibels lower than the reference. Then when we went for the grounded plate, so the one in orange, here we see a very substantial reduction, so an extra 12 decibels was obtained by this. And finally, the line in white or gray is with the large grounded plane. So this again added an extra 6 decibels. So it is possible to obtain some sort of shielding effectiveness with very small surface areas as long as these are properly grounded, and you might see this in real life in things like in the layout in guard traces, so simple traces of copper which are grounded, and these will provide some limited shielding effectiveness. You can go one step further by adding vertical plates on your board to protect some sensitive areas from some noisy areas, and this sort of plates can have dual function, so to be used on the one side as a heatsink for some sort of power transistor, but if they're properly grounded, then they will also provide a certain level of shielding. But in the end, the structure that will provide the best amount of shielding will be a completely enclosed space, so a proper shielding box. This will not allow any sort of E-fields or even magnetic fields to pass through it. But in any case, it is important to mention though that whatever shield you're building, it first of all has to be grounded, and secondly, the ground connection needs to be of very low impedance. And the lower the impedance, the better the shielding effectiveness going into higher frequencies. And with that being said, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.